So welcome. I'm excited to have the quarter with you guys. Before I start the lecture, I want to ask a couple of questions. First of all, how many of you are taking algorithmic game theory course at TTIC taught by Avril Blom this quarter? Raise your hand if you are. Okay. I assume that you guys are planning to come to this lecture as long as something interesting is happening here. Right? So question number 2, who wants to ascribe? So let me tell that first. As part of your grade in this course, you need to ascribe, which means that write a scribe note for our class, probably for 2 lectures, and then you have to revise 1 or 2 throughout the quarter as part of your grade, and then we will have what I call a midterm and a final, but they are really mini research questions that we'll be assigned to you to work on. So these are the 3 components that will be your final grade, and the scribe is probably like one of the most important ones. So what I'm doing every lecture is I ask for 1 or 2 volunteers so that you guys hand me the scribes maybe in 1 or 2 weeks, ideally. And then someone else is going to revise it. My idea is by the end of the quarter, we will have a nice set of scribes. So who is willing to ascribe today? Today is actually easy lecture for ascribing.
Sure.
All right, awesome. What's your name?
Andrew.
Andrew. Thank you, Andrew. And with that, let me start by just a brief introduction of what I'm gonna cover this quarter. So I have taught a PhD course on online optimization, which was basically online algorithm online learning before. This is a different iteration of that course, I would say. And the main difference is that I'm going to focus more on online learning. And as a result of that, I'm going to cover some stuff related to game theory. Basically, a good portion of this course is kind of like learning in games. And we will have a little bit of games in learning as well. You will see throughout the quarter. But there will be almost no focus on the theory of competitive online algorithms. So for those that you have seen the previous course, it is going to be slightly different from that. And then throughout the quarter, we will see some of the applications of online learning in different systems, ranging from dynamic pricing to recommendation systems. But I should confess that the course is pretty theory, so we are mostly going to have statements, lemma, theorems, proof. And at some point, every time that I see an application of what I'm teaching, I'm going to mention that. But the focus is on the foundation of learning theory and online learning. Any questions? Okay, all right. So let me actually start my lecture then. Does everyone see this part of the whiteboard? All right, so lecture 1. So the focus of today's lecture is basically on 2 main topics. So the first one is what I call full information online learning with finitely many arms. If you don't know the meaning of this phrase, you're sitting in the right path. And then the second part is how you can actually use online learning in order to solve zero-sum games. And in fact, how you can describe learning agents in a game when they're running online learning algorithm, full information online learning algorithm. So we're going to go step by step. And the first big step we are going to take is playing a game or trying to understand the game, which I'm going to call it reverse 20 questions. Let me start by telling you what the problem is. Are you guys familiar with the 20 questions game? Okay, pick a word. You have 20 questions to ask to guess my word. Right. So this is different. This is called reverse 20 questions. It's a kind of a weird game. So there is a player 1 and player 2. So player 1, let's say, picks the word from English dictionary, let's say, from a set S, where the cardinality of this set is equal to n. So think of it as an abstract object, a word that I pick from the English dictionary, and let's say English dictionary has exactly n words. Then player one, who picked the word, is gonna ask what I call sequential binary question. I pick the word and then I ask you, player two, from player two, I ask you binary questions of this sort. Let's say my word is X. So I'm gonna ask, for example, is X red? Or you can say, does X fly? It can be any arbitrary question, but it should have a yes or no answer based on the word that I have picked. So I ask player two sequentially these questions. And then after I ask each question, player two sequentially answers my question by yes or no. Either yes or no. All right. So every time that player two answers my question correctly, then he doesn't incur any penalty. But every time that he answers the question incorrectly, then he is going to incur a penalty of 1. So player two's penalty is basically equal to +1 if answers the question incorrectly. And it's going to be 0 otherwise. And let's say both player one and player two, they know the English language. So if they pick any word in their head, in principle, they can see whether that word is the answer of that question, a particular question.
Isn't the player two picking the word?
No, player, so that's the weird part.
Oh,
This is why it's called reverse 20 question. I'm going to pick a word, I'm going to ask you questions. I never tell you what the word is, of course. And then you have to guess whether the answer is yes or no. So,
Each time the game is player one asks a question, player two answers. It's not that like I ask
Right.
20 questions. And
that's true. That's what I'm going to
Okay.
put sequentially. Great. So it's going to be a sequential game. I'm going to ask a question, you're going to answer. I'm going to ask another question, you're going to answer something.
And player two observes their loss, right?
Then player two observes whether they gave a good question. So player two, after each round, observes the correct answer. Basically, they see whether they get +1 or 0. Observes the correct answer. The correct yes or no answer after each question. So the goal of player two, so what is the goal? So the goal is player two wants to devise a strategy that minimizes total penalty. And you can imagine that you're going to play this game forever. So you want to, first of all, you want to have a finite penalty, and second, you want to have actually a small penalty. Right? Is the game clear? Good. Let me try to form an abstraction of this game, which turns out to be helpful. So I'm going to define this new problem, which is pretty much the same problem. I'm going to call it binary prediction from experts, and in parentheses, which is kind of important, with and always correct. Always correct. Expert. All right, so let me formalize the notation, what this problem is. So we have what I call n experts. You have discrete time. t equal to 1 to blah, blah, blah. At each time t, imagine there is an adversary who picks a binary information, basically repeats, and repeats p of t, capital B of t, is revealed by an adversary, or basically selected by an adversary, is selected adversary. Right. So this information is not revealed to the algorithm or decision maker. So this is kind of something that the adversary is selecting. Now, each expert provides the algorithm with a so-called prediction. I'm going to use the notation BIT to be basically the prediction of expert I at time t. All right. Now, what happens? So at every time the adversary picks this bit, the experts go with some prediction about this bit. And then at each time, so let me write down the sequential thing that's happening. Experts give prediction. Now, an online algorithm that makes sequential decisions, I'm going to call it ALG, makes a prediction, predicts a t, another binary prediction, 0 or 1. So this small 0 is a Persian 0, in case that you guys are wondering. So in my native language, our zeros are small. Every time they get confusing, just remind me to make them a little bit bigger. So yeah, so the algorithm makes a prediction, and then ALG incurs the penalty, which is essentially, I'm going to call it L of t, which is equal to the indicator that he made an error. So AT is not equal to ET. And then PT is revealed. Sorry if you can't see this part, but basically nothing is really important here. So is the problem clear? There is a sequential game, there is adversary, there is an algorithm. At every time t, there are n experts, they first provide you with some prediction. Then the algorithm predicts a bit, incurs a loss if she was wrong about that original bit bt that was picked by the adversary, and then that bit is going to be revealed to the algorithm. Or you can say alternatively, the algorithm sees whether he made a mistake or not. That's a good one in the binary prediction. Okay.
So what would be the expert like a
Good. So in principle, these guys can provide you with any bit. It might be right or wrong. So be correct or incorrect. But then there is this parenthesis here. So for an assumption, I know as a fact that there is a bias expert. So there exists I star such that bi star of t is always equal to b of t for every t equal to 1 to no. So that's the most important assumption. So here's the question. Is it clear why the reverse 20 question is actually an example of binary prediction from experts' advices? Raise your hand if you see the connection. All right, so I'm going to ask Melissa. So do you want to explain this?
Like the always correct expert is like that word X. That was
The
just,
first thing is you have one expert for each word.
yeah.
Good. And then the correct word that I pick is actually the I star, the y expert. And what are the binary predictions? These PITs.
It is the answers, yes.
Exactly. So BT is the answer to this question given the correct word. And BIT is whether each word answers this question yes or no. Right? So some of the words that might accidentally answer this correctly, but then there is one magical word that answers all the questions correctly, and that's I star. And then the name of the game is that we divide an algorithm that kind of learn who is I star. In other words, wants to pick a sequence of predictions that make as many as smaller as possible. That's the right. Cool. But now, if you start thinking about this, you're like, well, there is one thing special about this problem, and that's the following. So every time that you make a correct yes, you don't enter any doubt. And then every time that you make an incorrect yes, then you incur a penalty. If you think a little bit, you're like, okay, so I wanna have an algorithm that sometimes makes a progress, somehow makes a progress, some sort of progress every time I make a mistake. Basically, every time I make a mistake, I would like to shrink down the set of uncertainty around the word X. In particular, S is your uncertainty set at the beginning, which is the set of all the English words. So you want to ensure that every time that you make a mistake, you can rule out a lot of words from this set, so that eventually, by the time that this set becomes empty, you haven't made that many mistakes along the way. Right? So that's kind of like the idea. And that brings us to this very simple algorithm. I'm going to call it majority algorithm. So what is the majority algorithm? So this algorithm is going to keep track of basically the majority votes. So what does that mean? So I'm going to say basically S of 0 is equal to S. These are all the correct, all the words in the English dictionary. And then I look at this set S, or S0, at each time t. I look at this set, and then I say, if the cardinality of the experts in this set such that they predict y, the 1, is more than the cardinality of the experts in this set that they predict 0, that means the majority of these guys are saying 1. Then I'm gonna announce 1, otherwise I'm gonna announce 0. That's the my prediction. Right. And then, but this is the first step, and then the second step, BT is revealed. And once BT is revealed, you know that some of these words couldn't be the word that they picked. You know, some of these experts were incorrect, so therefore they couldn't be ISL. So you update the set ST. So now ST is going to be basically T plus 1 is going to be ST set minus all the I such that BIT at that round was not equal to BT. So I kick out everyone who was wrong.
I think that should be ST, no?
You
No, the line above that.
this is ST, it's good. You're right. And you can see. Okay. Right. So now here's the claim. Let me make an abbreviation for this algorithm called NA. Number of mistakes and A is no more than floor of log capital N, it's log capital N. Actually, because let me make this a small n, because later I had this n here, so make everything consistent. So log n base 2. Right. The proof is actually pretty simple. So the proof is the following. Every time that you make a mistake, I claim that the size of this set is going to be shrink by a factor of 2 at least. Why? So imagine AT is not equal to BT. Therefore, the cardinality of the set of i's such that I in here, I in SD such that EIT is not equal to ET is basically the cardinality of I in SD, EIT was equal to AT. And because of the decision rule of the algorithm, we know this is very equal than the cardinality of I in SD, EIT was not equal to AT, which is equal to the cardinality of I in SD, EIT is equal to ET. So therefore, because the sum of these two is the cardinality of SD, I can say basically cardinality of SD plus 1, which is equal to the cardinality of SD minus the cardinality of all these i's that they made mistake. Is at most cardinality of SD divided by 2. Because this thing is at least cardinality of SD divided by 2. If I be a little bit more accurate, because these are integers, so you can say this is indeed the plural SD divided by 2. And now this will prove the claim. Why? Because you know that there is an expert that is correct because of the assumption. It implies that the cardinality of SD, regardless of 1, is always greater than 1 or greater than 1. So you can never kick out that. Right? So putting the two together, that means let me don't see the rest of the algebra. So we showed if AT is not equal to BT, then cardinality of SD plus 1 is at most half of the cardinality of SD. Let's say A is the total number of mistakes made by a majority algorithm. Therefore, I can say ST is always at most half to the power of A times the cardinality of S0, which is half to the power of A times N. At the same time, we know at every time is greater or equal than 1. So that implies that A, I already said that we can have a floor here. So that kind of implies that A is at most the floor of log N in base 2. And that's it. So pretty easy. Now, I will relax this assumption. That's the next step. What is that relaxed assumption? So rather than having a extremely wide expert, I want to assume that there is an expert that is not really awful, or in other words, it has bounded error. So that brings me to my other problem, binary prediction from experts' advice or experts with no assumption like that. So there are going to be two differences. So let me actually write down all the elements. So we have again n experts, binary predictions, etc. We have adversarial bit at every round. Everything is the same. Two differences. Difference number one, we are considering a finite game now. Basically, yes.
Good question. So this adversarial
Yeah.
assumption doesn't seem to play any role in the analysis.
No, so first of all, this is kind of like a deterministic algorithm, right? So there is no difference between what we call an oblivious adversary who picks these sequence of bits up front and an adaptive adversary that can change his mind on the way. That's the first thing. And then the adversarial is nothing but just like an arbitrary sequence of bits that is only revealed to the algorithm in another language. Yeah. Okay. Yeah, you could imagine that there was an underlying distribution that was generating these bits, but I guess this algorithm works regardless of the generative model for this data. Yes, sequence capital B. Great question. Okay, so the first difference is that now we're going to consider a finite horizon. So T is going to change from 1 to capital T. And then the second difference is that I'm going to relax that assumption. So I'm going to say there exists an I star such that some T from 1 to capital T indicator that BIT is not equal to BT, which is the total mistakes BI star T is not equal to BT. Right. Is at most some number n. So there is an expert with bounded number of mistakes given by the parameter f. Does it make sense? Now, the goal is the same. So goal is devise a strategy that minimizes total loss. And in the back of your head, you should know that even if you know who was I star, you couldn't do better than M in principle. I could give you a sequence of bits that this guy would have made maybe a mistake as large as M. But somehow, even though you are trying to minimize total loss, it would be kind of unrealistic to try to get an absolute bound, not relative to N. So therefore, kind of my goal prime is to devise a strategy that has total loss as close as possible to M. That's what you try to do. We try to have an algorithm that, regardless of T, capital T, gives you number of mistakes that is close enough to M. Yes.
Does the algorithm know M in advance?
Great question. Yeah, so in one version, I assume that the algorithm knows M in advance, but there are ways of relaxing that assumption. If I have time, I will tell you, and maybe we can chat about that. But that's a great question. A priori, I assume that the algorithm has information on that. there's parameter tuning that the algorithm needs to do, which requires knowing them. Rather than that, the rest of the algorithm I'm going to show you in a second is oblivious to the choice. Any other questions? All right. So now we had this majority algorithm, which is great. But when you think about it, no idea such as a majority like this seems to be applicable there because there is no notion of being 100% correct or not. And there is actually a version of the majority algorithm that you can devise. In the interest of time, I'm not going to talk about that version. Instead, I'm going to talk about a general version of this guy called weighted majority algorithm, which turns out to be helpful not only for this problem, but also a generalization of that problem, which is what I'm going to talk about after that. So let's talk about the generalization of the majority algorithm for that problem. I'm going to introduce this kind of natural generalization when you think about how to make this parametric to some sort of parameter to have more control over this half. You know, here the shrinkage was half, but sometimes you want to have more control. So if you're familiar with multi-arm bandits online learning, there's this notion of learning rate. Somehow this half is related to your learning rate. Now I'm gonna just generate this algorithm so that I have a parameter I can fine tune that gives me control over the learning. And the simplest way of doing that is this. So weighted majority algorithm. WMA. Right. So this is how this algorithm works. I'm gonna initialize a bunch of weights. W, let's say I at time 0, all equal to 1 for every expert time. Then at time t, for time t equal to 1 to all the way to capital T, remember now it is a finite horizon problem. Here's what I'm going to do. So I'm throughout this algorithm, I'm keeping track of weights for these experts. Previously, the weights I had were essentially 0 or 1, but now they can be other numbers. Then I basically see the total weight associated to 1 in the set of experts that I have, and the total weight associated to 0 in the set of experts that I have. And I go with the majority. What does majority mean? So I'm going to go with the one that has higher weights. So here's going to be my decision. So AT would be equal to 1 if and only if the following happens. If the summation of W IT minus 1 for all i's such that VIT is equal to 1, the total weight of the experts that predict 1 is larger than the total weight of experts that predict 0, then I would go with 1. Otherwise, I would go with 0. That's my algorithm. Now, in parentheses, so in this step, BT is revealed. Now that BT is revealed, I'm going to update my weights. What's up my update here? So here I was saying, hey, if this guy was wrong, I'm going to decrease the weight all the way to 0. And if it was correct, I'm not going to change the weight. Here I'm doing kind of the fractional version of that. And because of that, this algorithm is parametric with some parameter epsilon. So think of epsilon to be some number in the opening interval of 0 to 1. I'm gonna be a little bit hand wavy here and call this learning rate. Later on, when we talk about on-convex optimization, it will be very clear why this rate is called learning rate, but for now, just let's call it learning rate. All right. Now, given the parameter epsilon, here is what I'm gonna do. I'm gonna update the weights in the following fashion. I'm gonna say, hey, Wi P, which are the weights that I'm gonna use in the next round, would be equal to Wi T minus 1 times 1 minus epsilon. What will be the exponent here? So it's gonna be the indicator that the guy was wrong. So if BIT was not equal to BT. Okay, so this is the fancy way of writing down the following. So if the expert was correct, I'm not changing the weight. If the expert was wrong, I'm going to multiply the weight by 1 minus epsilon. And the majority algorithm is a special case when epsilon converges with 1. But now I'm allowing arbitrary learning. All right. Is it clear what the algorithm does? And the kind of like the logic behind the design of algorithm. Because I think one thing I really care about in this course is you guys understand the logic behind designing this algorithm, not just like seeing them and memorizing them. All right, so now we wanna prove our maybe first proposition or theorem in this class, because that one I don't think is counted as real results, but this one is actually real results. Proposition. Let me add one more definition. Maybe I don't. Yeah, that notation here. The proposition, if A is equal to the number of mistakes of weighted majority algorithm with parameter epsilon for some epsilon in 0, 1, then the following is true. Then we have the following. I can say A, which was the total number of mistakes, we expect this going to be balanced. That's going to be what this proposition is. And we somehow expect that the bound to give us something close to M. But the bound I'm going to write is going to be a little bit disappointing. So A is going to be at most 2 times M divided by 1 minus epsilon plus natural log of N divided by epsilon times 2. So A is going to be at most 2 times the number of mistakes of the best expert divided by 1 minus epsilon. And this 1 over 1 minus epsilon is basically 1 plus order epsilon. So if I want to write this bound in kind of asymptotic version, this is essentially 2m plus order of m epsilon plus ln of n divided by epsilon. Right, because 1 over 1 minus epsilon is something like 1 plus just 1 plus epsilon over 2 and therefore you get a 2m, and then you get order m times epsilon from this guy, and the rest from this guy. So back to your question, if we know what m is, then we can have this corollary. if we set epsilon to be, let's say, the square root of ln of n divided by m, knowing m, then what happens is that a is going to be at least 2m plus. First of all, how did I pick that epsilon? Kind of balancing these two terms. Because if you increase epsilon, then this guy increases, this decreases, and vice versa. So if you balance the two terms, this is the best choice of epsilon in asymptotic. That means epsilon squared should be equal to ln of n divided by m, or in other words, epsilon is the square root of ln divided by m. So a is going to be at most 2m plus order the square root of n times ln. This is the bittersweet result, because on one hand, you're happy because this term seems to be much smaller than m, is order the square root of m. Ignore this log n term. But at the same time, it's disappointing because of these two. Right? So you expected that you get close to m, not 2m. So this makes me unhappy, but then this makes me happy. Good news is, next thing I'm going to show is how to get rid of these two while we maintain this square root dependency on m as an quick term. But for now, let's actually just prove this and then we get to the next result. And you will see one of the few examples that I know that randomness, in the world of online learning, in the world of online algorithm compared to online algorithm, randomness is brilliant. Many times you can pass information theoretic barriers that the deterministic algorithms face by just using randomness. But when it comes to learning, and you will see what I'm saying later, that usually randomness does not bring you that much. What I'm going to show next is an example in which randomness gives you extremely huge power. And in that case, it's going to help you to get rid of these two. But for now, let's try to prove this proposition, which would be the first step to prove the final proposition and the main algorithm of today's lecture. All right, so proof. When I was preparing this lecture, I realized I know 6 proofs of this statement. And some of them are using potential functions, some of them are using results from online linear optimization, some of them are using actually ideas related to calibration, which I'm going to talk about in the next lecture. And I was really undecided what proof should I pick. So I decided to actually go with the version I learned when I was a grad student and my advisor was teaching a similar course. It's not the easiest way of proving this proposition. If you are an expert in convex optimization and you're familiar with first order methods, and you heard the word online linear descent or follow the regularized leader, there is literally a 3-line proof for this statement by using a black box off-the-shelf result from that literature. But I think this proof still sheds a lot of insights about why people even came up with this algorithm at the first place. So because of that, I decided to pick this proof. I think it's actually quite nice. So the main idea of the proof is using what I call a potential function argument. And if you haven't seen potential function arguments, I think this is kind of a canonical example of a potential function argument. So you can learn. Next time someone mentioned it, there is a proof by potential function, and yeah, you can think of it. So what is a potential function? A potential function, you already actually saw one example of potential function argument. In the proof of the majority algorithm, we were keeping track of the size of the set of experts that are not incorrect so far. That's actually a potential function. So you were keeping track of how the potential function changes as the algorithm makes decisions. And you also had an invariant which was that the size of the potential function should be always lower bounded by 1. So combining the two pieces, you could bound the number of mistakes made by the algorithm. This is kind of the essence of any other potential function. So here we are going to do something similar. And the most natural analog of that potential function shows the size of the set of correct experts is.
For potential function
Yeah.
arguments, are they always like, you have some number and you want it to like shrink?
Typically, yeah. So what's going to be the analog of the potential function here? So remember, in the majority algorithm, we had the weights which were 0 and 1, and we were looking at the cardinality of the set of correct experts. What's going to be the analog here? We'll do something similar.
Some of the weights.
Some of the weights, right? Okay, great. So I'm going to define this quantity, capital WT, which is the sum of the weights of all the experts. So it's going to be summation of WIT or I in N. And now we are trying to understand this quantity. First, we are trying to understand whether this quantity is lower bounded by something related to hopefully M. And then second, we are going to keep track of how this quantity changes as the algorithm makes decisions. Right? So play number one, which is kind of easy. W at the end, and in fact W at any time, is going to be bounded by 1 minus epsilon to the power A, where A is the number of mistakes that the algorithm makes. Let's see why. Proof. So WT at any time, including time capital T, is always greater equal than W of my special expert I star, who makes at most n mistakes. It's going to be at most W I star of T. You know, all the weights are positive. They, in fact, always are between 0 and 1. So I can just exclude those that are not corresponding to my quote-unquote best expert. And then I have this trivial inequality. But then this guy doesn't make mistake more than capital M. It doesn't make mistake more than capital M number of rounds. Right? And every time that it makes a mistake, a weight that is started at 1 is going to be multiplied by 1 minus epsilon. So therefore, the smallest quantity that this can get would be 1 minus epsilon to the power. And here. But this is capital, not but algorithm. Algorithm is going to control the way that WT changes throughout the run of the algorithm. Now, we want to see how does WT changes over the course of running the algorithm. So let's think about WT plus 1. But this is nothing but just a summation of I, let's say WIC plus 1 for all the experts. And then this guy is equal to the summation I in N WIT times 1 minus epsilon to the power of the indicator that basically BT is not equal to BIT. Now you can write it down as a summation I in N. Summation over all I such that BT is not equal to BIT. And then you will have WIT times 1 minus epsilon. And then for the rest of the experts, you only have WIT. It's pretty much the analog of the proof of the majority algorithm. Now this is equal to summation of WIT for all I in N. All I did was merging this term with that term, minus epsilon times the summation for all I such that BT is not equal to BIT, WIT. Is this clear? Now I want to claim that every time that the algorithm makes a mistake, this quantity, let's understand this one. Let's assume that you're at some time t, assume at time t, AT is not equal to BT. That means that the algorithm has made a mistake in that round. If that happens, what does that mean? So that means that some of the weights of the experts corresponding to BT was actually smaller than the set of the sum of the weights for experts corresponding to 1 minus BT in a binary. Right? So let me write it down. So if that happens, that means the summation of WIT for all i's that the VIT was equal to BT, the correct one, turned out to be smaller than the summation of WIT for all i's where VIT was not equal to BT. Otherwise, you wouldn't have made a mistake. And then we know that all of these two is equal to, let's call this x, let's call this y. So we know x plus y is equal to W, capital WP. So therefore, we can conclude that if there is a mistake at time t, the summation of WIT for all I where BIT is not equal to BT is at least WT divided by 2. Are we all good? So this is kind of like the analog of the previous analysis. So now I'm going to say, if AT is not equal to BT, then this is going to be at most WT times 1 minus epsilon divided by 2. So you will have a shrinkage of the potential function every time that the algorithm makes this. And how much you will shrink the potential function? This time, the learning rate gives you a control over that. So it's going to be shrink by a multiplicative factor of 1 minus epsilon divided by 2.
It's at most, no?
At most, you're absolutely. It's shrinking. Thank you. Yeah, so this is at least WT divided by 2. Therefore, the next W is going to be at most W squared by minus epsilon. Right. Cool. So this is stuff. Continue. So therefore, I have claim number 2 instead of the following. W at the end would be at most 1 minus epsilon divided by 2 to power A, where A is the number of mistakes made by the algorithm, times W0. And W0, remember, so we are initializing at 1, so this is nothing but just 1 minus epsilon divided by 2 to the power A times N. And the proof is essentially the same thing. So every time that you make a mistake, your initial value or previous value will be multiplied by 1 minus epsilon or 2. So if you make any mistakes by the end of the horizon, which is the assumption, which is the definition of A, that brings WT at most all the way to 1 minus epsilon over 2 to the power A times the initial value. And initial value was N. All right. So far so good. Let's put the two pieces together to claim our results. So putting claims 1 plus 2 together. We have an upper bound on WT and then lower one on WT. So that means 1 minus epsilon over 2 to the power a times n is greater or equal than 1 minus epsilon to the power m. So let's take a natural log from both hand sides. And then that means ln of n plus a times ln of 1 minus epsilon over 2 is greater or equal than m times ln of 1 minus epsilon. So that brings me to my favorite inequality about natural logarithm. Let me actually describe that over a picture. For people who have taken a course in information theory, the picture I'm gonna draw and that inequality is kind of like the first thing that they usually teach when they wanna tell you what is the limits of compression using asymptotic equipartition property. So this is, I don't like, first time I saw this inequality, I was like, I will never use it in my life. Maybe it is only applicable in this example. Last time that I used that was actually when I was writing a paper with Farwell a few weeks ago, and we didn't know how to prove an inequality, and then it turned out to actually be helpful. So what is that inequality? Let me actually draw a picture. So natural log is a monotone concave function. It's like ln of x. And the heating point when it becomes 0 is x equal to 1, as we all know. Now, if you draw a tangent line to ln of x at this point, and you continue this guy, this is a really bad picture. But it turns out that this is equal to 1 as well. So this is 1 and this is 1. In other words, ln of x is always upper bounded by x minus 1 for every x that is strictly greater than 0. Basically any x. And the x greater than 1 region is helpful, the x smaller than 1 region is also helpful, then natural log becomes negative, and you're gonna see that in a second. All right, so what I'm gonna do is trying to use that inequality several times. And by the way, so proof of this is easy. At x equal to 1, they're equal to each other. You can take a derivative from both hand sides and double check that the derivative of the right hand side is smaller than the left hand side is smaller than the right hand side for both x greater than 1 and also x smaller than 1. So hence the proof by taking integration. All right, so now I'm gonna say, well, if I want to use my inequality, this is going to be at most minus epsilon over 2. Remember, it doesn't matter whether this is negative or positive. So 1 minus epsilon over 2 is always at most minus epsilon over 2. So now that means a times epsilon over 2 is at most ln of n minus m times ln of 1 minus epsilon, which is equal to ln of n minus m plus m times ln of 1 over 1 minus epsilon. And this is equal to ln of n plus m times ln of 1 plus epsilon divided by 1 minus epsilon. And now I'm going to use that inequality again. So this is at most ln of n plus m times epsilon divided by 1 minus epsilon. Now rearrange the term to get the result. Result of that, A would be at most 2 times ln of m divided by epsilon plus 2m divided by 1 minus epsilon. And that's fine.
So I'm trying to understand the intuition behind the potential function.
Mhm.
It arises in many places. So initially you wanted to find an upper bound on A, right? So the utility of potential function is that you sort of take an exponential function of the objective, which is A, and then find the lower bound on it. Because it seems that in plane 2, you have the objective function that you wanted to upper bound sort of exponentiated with some
That's true.
basis, and then you find an upper bound on it.
Yeah, so
So in
your
order to
point
find a
is
lower bound.
kind of like log of the potential function in the right basis is a lower bound on the algorithm. That's true. And this is, I mean, you need a potential function that measures the progress. That's how I think of it. That you make you have an algorithm. Here it's not progress. It's actually you degrade in the sense that you're going to incur penalty. So you want the potential function to measure that negative progress. So therefore, you're better off having a potential function that in a monotonic way is related to A at the door. So basically, that potential function should, in a monotonic way, should form a lower bound for your algorithm. Turns out that exponential function is helpful here. And if you're curious why on earth exponential function is helpful, it goes back all the way to that description of this algorithm using unlinear descent.
Yeah.
It turns out that unlinear descent, when you use the regularizer term, which is negative entropy, will give you exponential base, which is another fancy name for weighted majority algorithm, or the one that I'm going to show now, randomly weighted majority. And there is a fundamental reason of why you actually need potential functions of that nature. Right? And so there is a systematic way of coming up with mirror maps. They should have some properties, and then when you add the certain properties that you want, in fact, the negative entropy comes out of that. At some point in this course, I'm going to get to that as well, how to design mirror maps and how to get meaningful rigor bounds under different structures with the help of the mirror map. Here, I didn't talk about those because it's like too early. But this is a great question. You got it.
What's the tie breaking for here? If
Here, it is like, doesn't really matter. I think I intentionally wrote it in a way that there is no tie, right? So my algorithm was, I erase the algorithm. If one is a tricky larger than the other one, you go with 1, otherwise you go with 0. And if they're equal, so you go with 0. But essentially, it doesn't really matter. Okay. So now the question is how to get rid of these 2, which seems to be very annoying because even though the additive term is small, you're losing a multiplicative factor. In many applications, this probably is more harmful than a larger additive factor. So that brings me to my next algorithm. And this algorithm is going to use randomness in order to pass this value. Why we need randomness? I think the reason is because the underlying problem we are solving, even though we have n different experts, I'm going to call them arms in a second, and you are picking it seems you are picking a discrete object, which is one of these arms. Essentially, what you are picking is a point in an n-dimensional simplex, which is the distribution over these arms. It turns out that here you are fine with picking point masses, but in principle, really you're solving an nonlinear optimization problem. Whereas in the decision maker, you're picking a point in the n-dimensional simplex, and then you incur a loss, and you would like to minimize the loss. So maybe by picking points inside the simplex, you can do better, and this is exactly what we are doing. Right? So before that, let me describe a new problem. I'm going to call it full information adversarial online learning with finite remaining arms. And you see in a second that this actually generalizes the binary function. So what is this problem? We have n, I'm going to call them arms. Think of them as the experts. Each arm I, so we have discrete time. So discrete time t from 1 to capital T. Bounded horizon, undiscounted problem. There's a variant of this that considers geometric discounting. I probably won't get there, but I'm happy to talk about that offline. But this is undiscounted future in some sense. You have finite horizon, and then each arm I is associated with a loss. At time t, which I'm going to denote it by L I T, and let's actually normalize these losses so that they are between 0 and 1. So this is going to be the timing of the events. Can you guys see the part, or should I write down? Okay, so at each time t from 1 to capital T, first, the algorithm selects one of these arms. I'm going to call it IT. Then loss of the algorithm would be equal to L of IT of T. That was the practice. And then all losses are revealed to the algorithm, which is the vector LIT for all IE. So this is now a loss minimization problem. At every time t, you have n different arms, you pull an arm. When I say select an arm or pull an arm, that essentially means that you pick an integer from 1 to n, corresponding to that arm, the index of that arm. And then the algorithm incurs a loss, which is the loss of that arm at that time, denoted by LIT of t because you picked IT. And then after that, you receive full information feedback. And this is the reason that this thing is called full information adversarial online learning. So this is going to be full information feedback, which means not only you receive the loss of the arm that you pulled, but you also receive the losses of the arms that you haven't. So you see the entire vector, the loss, which is a little bit unrealistic, but this is going to be the right baby step in order to design algorithms that they only get to see the loss of the arm that you pulled, which are adversarial multi-arm band algorithms. And they're going to get, but for now, let's assume that you have full information. That's one note. The second note, to be honest, I think the right way of looking at this problem is really a two-player game played between an algorithm who is selecting arms and an adversary who is actually selecting these losses. And back to Parshall's point, here we have a lot of power. I'm going to assume that my adversary is actually an adaptive adversary. I don't even need to restrict myself to oblivious adversary. So the adversary not only knows the algorithm, the decision rule of the algorithm, but also it gets to see the random coins of the algorithm, the exact realization of the arms in the previous times. So imagine that I'm playing this game with Muhammad, so he decides on some loss function to make me incur a penalty. Then I pick an arm. Then we go to the next round. He knows what arm I picked in the previous round. So based on that, can change the loss function in the next round. So on and so forth. So this is an almighty adversary or adaptive adversary. There is also another variant, which is an obvious adversary. That means Muhammad at time 0 should commit to a sequence of loss functions for all time for all arms. But that's not, I mean, we can, I can't even fight against Almighty Muhammad. That's not what they would do, but and so we make no assumption that the adversary will now, another note. Is it clear why this generalizes the binary prediction function? Imagine losses are either 0 or 1. And the loss function is defined in the following way. So let me have this arrow here. Binary prediction is a special case when my loss corresponding to expert I at time t is basically the indicator that BIT is not equal to ET. So rather than getting to see capital B and all these predictions, alternatively, I could just like see this information and you could run the weighted majority algorithm. If I knew which experts were correct, which were wrong, that was the only information I needed in order to run that algorithm. And this is essentially that information. So you need that information to be revealed in full after each decision-making round, hence the full information feedback. But you don't really need the other micro foundations of that problem. It generalizes very, very easily. Is it clear like why this is generalizing binary prediction problem? Now, one other question. How do you guys feel about having a short break maybe after I told you what the algorithm is? Then we can resume in like 7-8 minutes after. Sound good? Yeah, so this algorithm has so many names. Let me actually write all of them in case that you see that name somewhere. It should remind you that this is actually the same algorithm. So the first name related to our lecture is randomized weighted measures. That's kind of the big name. And then it's also called multiplicative weight update, or MWU. It many times goes with the abbreviation. Sometimes it's called HEDGE. And you will see in a second why it's called HEDGE. Sometimes it's called follow the regularized leader with negative entropy. Sometimes called online mirror descent. And you don't need to know what are these things. I'm going to explain them in lecture 6 or 7. Again, with negative entropy. It has 2 other names, exponential base and the last one is EGA. This is actually descent, EGD, exponential gradient descent. And even though when you look at a certain book related to different areas in machine learning, you might see these different names and different descriptions. They're all the same algorithm. Not even under this slide, under the book. This is literally the same algorithm. But because of historical reasons, people have rediscovered this algorithm many times in different contexts. And because of that, you see all these different things. Right? So what is this algorithm? You will be surprised how simple it is, how it is connected to weighted majority. It's literally weighted majority, but now that you keep track of weights, rather than going with the majority, draw an arm randomly with a distribution that is proportional to your weights, and play that. That's it. And then keep the weights updated exactly as before. So HEDGE with parameter epsilon. This is the algorithm. I'm going to initialize my weights. Wi0 to the equal to 1 for every arm. Then for every time t from 1 to capital T, do the following. First, I'm going to define a distribution. Yes, so define this distribution. Let's call that P of T, which is a point in the n-dimensional simplex. So what is this notation? So this is basically the set of all vectors x in, say, Rn, such that summation of xi over I in n is equal to 1 and xi is greater or equal than 0. The set of all discrete distributions over n different functions. So this PT is the following. So PT is going to be equal to Wt, the vector of weights that you have, Wt minus 1, the vector of weights from the previous round, divided by basically Wt minus 1 dot product with the vector of all ones. And this is just fancy way of writing down PTI is equal to WTI divided by summation of WTJ over all j in n for every arm I. You normalize the vector by L1. And for the experts of Archimedes linear descent, this is basically projection using using Bragg divergence with negative entropy, which is equivalent to finding a point in the simplex that minimizes the L1 distance, not L2 distance, L1 distance. If you have a vector, let's say W, that is not necessarily a distribution, you want to find the distribution, you want to kind of do project into that space. If you do projection with respect to L1 distance, that is equivalent to finding a point in that space that minimizes some sort of distance called Bragg divergence. And Bragg divergence is parametric with some function. That function is going to be negative entropy. This is why this negative entropy appears here. And this whole complicated thing is equivalent to normally. So now that you have the distribution, draw an arm IT from this distribution PT, play that arm. So you're going to incur a loss which is equal to L of IT and T, and then update the weights. So WI2 plus 1 would be equal to WIT times 1 minus epsilon to the power LIT. And then we write down my theorem, and then we will have the range. So theorem, if A, which is now a random variable, is the number of mistakes, well, not the number of mistakes, right? So if it is equal to the summation, let me actually use a different notation. If A is equal to sum from T from 1 to capital T of L, I, T, and T, the total loss incurred by algorithm HEDGE hedge of epsilon, for some epsilon between 0 and 1, then you have the following expectation of A is at most m divided by 1 minus epsilon plus ln of m divided by epsilon, where m is the loss of the best expert. So this is basically the minimum over all I in n, summation t from 1 to capital T, Lit. So you look at all of these experts. So there is one of them called the best fixed expert or best fixed R. So I star is going to be the arc mean over all I, from T from 1 to capital T, L of I and T. So M is equivalently equal to summation of Li star. T from 1 to 2. And our goal is to be as close as possible to M. For the special case of binary prediction, this is the best expert. And as you can see from the theorem, the corollary is that expectation of A now would be at most M plus order of M epsilon plus log of n. So we got rid of that factor. So let's say we have 6-7 minutes. So we will be back at 10:32. And we are going to see how to prove this theorem very briefly, and then we switch to zero functions.
Okay.
So proof. It's almost an identical potential argument. So almost identical potential function argument as before. But I should say that it has some subtle differences that makes a huge difference. And before, I'm going to define a potential function. So my potential function, again, is the summation of the weights, exactly as before. So Wt is defined to be the summation of Wit for every I in. One difference, though, so I assume that my adversary is adaptive. So that means the adversary, looking at the previous algorithm decision, can decide on the last vector. So therefore, algorithm decision in the past would change the last vector at every time. And that changes the weights. And then algorithm is randomized. So therefore, these weights, in principle, they can be randomized. So the randomness comes from the fact that you are running a randomized algorithm and the adversary is adaptive. If the adversary was oblivious, then nothing was random. It was, again, deterministic. But assuming that you have a randomized algorithm, in principle, and an adaptive adversary, these guys can be random variables. So the first argument is the following, that if I look at Wt, again, as a random variable, I can say it is greater or equal than a small w I star t, I star capital T. So what was I star? It's the arm, the best fixed arm in hindsight, the guy that has the smallest total loss. And based on the definition of the weights, exactly as before, this is going to be at least 1 minus epsilon. Now, every time that this arm incurs a loss, it's going to appear in the exponent. So if you multiply them together, you get the sum of the losses. So it's going to be summation Li star t for t equal to 1 to capital T, which is equal to 1 minus epsilon to the power m based on the definition of m. First step, exactly. And then we have another claim too. So I'm gonna keep track of expectation of Wt plus 1 condition on, say, Wt.
I think this M should hold for with probability 1, right? Because it seems you're using it for any realization of L.
True. Okay, so you're absolutely right that I was a little bit sloppy here. M, yeah, M is the realized loss. In the theorem, let me actually add an expectation here. So the adversary plays the game until the end, and then I decide who is the best, right?
Right.
So yeah, so this whole pointless. For every sample path, you have this inequality. The other one I'm going to show you is not true pointless. It's actually true in expectation. But that one is true in pointless. Yeah. This random that I'm adding is just a layer of complication to allow handling adaptive adversary. If it makes it complicated for you guys, just imagine that these losses are deterministic. It doesn't really matter much. And then these expectations in some sense are unnecessary, but I want to show you one example that how you can handle adaptive adversaries. And yeah, let's do with the expectation version. And then this is equal to expectation of summation I in n WT plus 1. Was it WIT or WTR? IT. The WI plus 1 condition on WT, which is equal to the expectation of summation I in n WIT and 1 minus epsilon to the power LIT condition on WT. And this WT is basically it. All right. So far so good. Now I'm going to use particular inequality. Here's the inequality I'm going to use. Imagine epsilon is a number between 0 and 1. Then 1 minus epsilon to the power x. And x is also a number between 0 and 1. So imagine x is between 0 and 1, epsilon is between 0 and 1. Then 1 minus epsilon to the power x is at most 1 minus epsilon x. I'm not going to prove that to you guys, but you can guess how you should prove it using that magical inequality using log function. Take a log and try to prove that as an example. There is a direct way of proving this as well. Now, if I use that inequality, this is going to be upper bounded by expectation of some I in n WIT times 1 minus, so 1 minus epsilon to the power L. And remember, I assume the losses are normalized to be between 0 and 1. So this is going to be multiplied by epsilon times LIT condition on WT. So now, you can decompose it into two terms. The first one is going to be the sum of the previous weights. And because you're conditioning on the previous weight, this is going to come out. So it's going to be WP itself minus epsilon times the expectation of summation over all I WIT LIT condition on WT. It was really the step that the magic happened from here to here, the first magic. And then the second magic is going to be here. So now, what I'm going to do is I'm going to divide this by WT, and I'm going to multiply this by WT. Remember, because it's conditioning on the previous weight vector, so now it seems you should treat this as a deterministic number. So this is what I'm doing now. So this quantity now is familiar. So the weights divided by the sum of the weights is the distribution that the HEDGE algorithm is drawing Armstrong. This is nothing but PIT. And therefore, this whole thing will be WT times 1 minus epsilon times the expectation of, let me write it down, L I T and T conditional WT. Why? Because, well, so this summation is now an expectation itself. Because you're summing over all arms, multiplying by probability of putting that arm times the loss that you get under that realization. So this is the expectation of L, I, T, and T. And we have a condition on the details before, hence this term up there. Make sense? Now, what I'm going to do is I'm taking a log from this, which is the right-hand side, and this, which is the left-hand side. Let me write it down. So natural log. So Ln of expectation of WT plus 1, condition on WT, now would be at most Ln of WT plus Ln of 1 minus epsilon times expectation of LIT T condition on WT. So here I'm going to use the so-called Jensen inequality. Jensen's inequality. The log is a concave function, so the log of the expectation will be more than expectation of the log. The geometric picture. So this is log. So if you have these 2 points, you look at the convex combination, let's say somewhere here, and convex combination here, then DC is going to be below this, right? So that means the log of expectation, which is this point, is larger than the expectation of the log, which is but now this is going to be greater than the expectation of the log of W T plus 1 condition on vector WT. And here you have this familiar term, Ln of 1 minus x. And we already know how to handle that. So it's at most minus x. So this term, based on that magical inequality, is going to be at most minus epsilon times expectation of L, I, T, and T condition WT. Rearranging the terms, you get the following. So expectation of Ln of WT plus 1 minus Ln of WT condition on the vector WT is at most minus epsilon times the expectation of the loss of the algorithm at time t. And partial. So this is kind of related to the point that you mentioned in the previous analysis. We came up with a potential function that after you get a log, the amount of progress is a lower bound on the loss that you incur with the learning rates bounding the ratio between the two. And this is essential in this argument. And in the analysis of online gradients and the analysis of online gradients and so on. Everything in first order optimization, you see this inequality in some form appears. Sometimes in a more cryptic form, but it is really a potential functional argument in this. Now, every time that you see the difference of 2 terms where the index of this is greater than the index of that, the first thing that you want to do is sum them up from t equal to 1 to capital T so that there will be telescopic cancellation. And this is exactly what I'm going to do here. So sum t from 1 to capital T, maybe t from 0 to actually capital T minus 1 to be exact. You're going to have the following expectation of log of W capital T, which is the last term, minus log of W0, the first term, would be at most minus epsilon. Wait a second. So I think Oh, so loss T is used for. Maybe that's fine. From 0 to T minus 1. Okay, loss is between 0 and loss, and T equal to 0 is nothing, so I just add the last term as well. I'm just adding the last term that is missing in my summation, which is okay, because the losses are between 0 and 1. So T now from 1 to capital T. So this should be T from 0 to T minus 1. There is no T equal to 0, and then you can add the 1 at capital T because losses are non-negative, so you have to avoid this. So what is this term? So this is the log of n because the original weight is Ln, is n. Rearranging the terms, we kind of get the analog of the previous result. So we have epsilon times expectation. Sorry guys. I did a couple of things in my head. I didn't mention that. So from here to here, first take an expectation over WT so that you get rid of this. So let me be presets. I first take the expectation here. So that will cancel this WT here. Once you took the expectation, do the telescopic summation, and therefore you get this. Right? So first take expectation so that you don't have any conditioning anymore, then do the telescopic summation, and then you're good. So now rearranging the term, the epsilon term, the expectation of essentially A, the loss of the algorithm, is at most expectation is at most ln of n minus ln of WT. Good. And then we know WT is at least 1 minus epsilon to the power n. So therefore, this is at most ln of n minus m times ln of 1 minus epsilon. I haven't made any mistakes. Yes. And this is equal to m times ln of 1 over 1 minus epsilon. And we use the trick as before. So this is going to be ln of 1 plus epsilon divided by 1 minus epsilon. And it is at most epsilon over 1 minus epsilon using the magical inequality. Therefore, the whole thing is going to be at most ln of n plus m times epsilon divided by 1 minus epsilon. Now you see the epsilon over 2 here is now epsilon. That's the magical part. Therefore, rearranging the term, expectation, and this is expectation m. I'm sorry, because the way I defined m was for every realization, so you need to take expectation after, so it's expectation. So therefore, the expectation of the algorithm is going to be at most ln of n divided by epsilon plus expectation of m divided by 1 minus epsilon. And we are done. Right. You might wonder how tight is this out? Whether any algorithm can do better than that. I'm not gonna show, so there are two lower bounds here. First one I'm not gonna show. The first lower bound is that no deterministic algorithm can do better than the weighted majority. So that's factor 2 is fundamental, so you can't get rid of that without using randomness. The second lower one is easy. The bound that I'm gonna get in the corollary is actually information theoretically tight for any algorithm. And let me actually tell you what that bound is. And that brings me to the definition of regret. So corollary expectation of A, the total loss of the algorithm, is at most 2 times the square root of t times ln of n. How to show this? Right, so let me show you a simple proof of this fact by a particular choice of epsilon. If epsilon is selected to be a square root of, I think, ln divided by t, I might change the constants later. So proof, this is the result that we have if you kind of like rearrange the terms the same. So multiply both hand sides by one minus epsilon, so you will have 1 minus epsilon times expectation of A is at most 1 minus epsilon divided by epsilon times log of n plus expectation of m, which is at most ln of n divided by epsilon, just like replace this 1 minus epsilon with 1 plus expectation of m. Now, if I move things around, sorry, this is the expectation of A minus expectation of n. Yes, so that becomes this. I'm sorry, this is the regret now. Expectation of A minus expectation of n. So if I move things around, that means expectation of A minus expectation of m would be at most epsilon times expectation of A plus ln of n divided by epsilon, which is at most, because losses are bounded by 1, so expectation of A is bounded by t, so it's going to be bounded by epsilon t plus ln of n divided by epsilon. So now setting epsilon to be the square root of ln of n divided by t, this will become 2 times the square root of ln n times t. Right? So this quantity, which is kind of alg minus opt, I'm going to refer to that in this class as the regret. In fact, for this full information adversarial learning problem, the regret is defined to be the gap, the additive gap between your algorithm that is minimizing the loss and the best fixed arm in hindsight. By a star, which is the arm that if you play in all rounds, the same arm, minimizes the total loss. Right? And this corner is bounding the regret. So as well, so even though you're playing in capital T number of rounds, the total loss you accumulate is growing at the rate of the square root of t, which is great. That means on average over time, this is vanishing. So sometimes the algorithms like HEDGE and also weighted majority that gives you this kind of bounds, they're called vanishing regret or no regret learning algorithms because on average, their loss versus a benchmark, in this case, the best fixed arm in hindsight, converges to 0 as horizon goes in. Right? That's one thing. The other thing is, this is fundamental. No one can do error run. No online algorithm, regardless of being deterministic or randomized, can do error run this bounds. This information theoretically intact. And let's see why that is the case. Let me use this as a for lower bound, and then we're going to go there and talk about zero sum games. Lower bound. So let me wave my hands a little bit and leave the rest of the calculations to you guys. Imagine the following problem instance. Suppose all the losses are symmetric Bernoullis. Basically, LIT for any arm at any time t is basically Bernoulli with probably half. So it is either 0 is probably half or 1 is probably half. And let's say they are all IID across arms, across time. So there is this adversary who is like flipping coins, symmetric coins, and you get to see the outcome of the coin as the online outcome. So your online, that means when I'm at time t, I only have observed history, so I don't know anything about what I'm going to see at time t. And it doesn't really give me any information about time t because the loss at time t is independent from the past. So no matter what I do, whatever R I pick, in expectation, in every time I'm going to incur a loss of one, a loss of time in expectation. Whatever R I pick, we probably have I'm going to get one, probably I'm going to get zero, and I cannot get away from it. So any online algorithm will have an expectation, expected loss equal to T over 2. However, if you look at the sequence of coins, look at the best R. There's one expert that has the minimum number of ones. Right. So I claim that with high probability, there always exists. So claim with high probability, there always exists some I star such that the realized loss, the summation of Li t for that I star t from 1 to capital T, is no more than something like t minus 2 minus a square root of ln times t. This is a very simple logic regression now. Essentially, it says that even though these random variables are going to get concentrated around T2, and whether the random variables I'm talking about, the total loss corresponding to different arms, but there is still enough probability that they land in the tail if you are away enough from the mean. And it turns out that this is actually enough in order to get that. So I'm not going to show you the exact proof, but the proof is pretty simple. So basically, we use PLT. Proof use CLT, central limit theorem. So you know that the summation of these Bernoullis in distribution is going to converge to Gaussian. Then find the tail probability, the probability that X, which is the total loss, is smaller than T over 2 minus your gap alpha, where alpha is this number. Then use union bound. And once you do the combination, you can easily show that this event happens with high probability. That there exists an arm that is deviated enough from mean. And by enough, I mean by the distance of the square root of ln of n times. So therefore, this is fundamental. Any online algorithm will incur regret, which is order square root of ln times t. If you're wondering, is two is tight, it's not. And there is a line of work. They try to pin down the right constant. If you're interested, I'm happy to point you to those papers. You can take a look. It's actually pretty deep. So how to get this right? And it turns out that there is actually an online linear descent algorithm that can give you the best constant. We have engineered here, which is kind of cool. So any questions? Yes, Pasha.
I have one question. So typically the regrets I've seen don't have this expectation over M. So here the expectation comes for M because of allowing adversary to be randomized.
Exactly. So
And your expectation of A is with respect to your randomized decisions, right?
any randomness involved in the problem, including the randomness used by the algorithm and the other.
Oh,
I think the right way, as I said, the right way of looking at it is the two-player game played between algorithm and adversary. Both of them, in principle, can have randomized strategies. And these expectations are over all the randomness.
oh, okay.
Even here, the randomness in the algorithm appears, right? Because I'm an adaptive adversary, I can look at the algorithm's previous decisions, and based on that, change the distribution I'm drawing a new loss from. So the expectation over the whole space. Great question. All right. So this is cool. This is going to help you to kind of learn from expert advisors, learn in an environment that you put no restriction on the loss vector as long as you have full information, which is pretty essential. Now, I'm going to show you one or maybe two applications of this, in particular in game theory. And the story is the following. So first of all, how many of you are familiar with very, very basics of game theory? Like what's the definition of normal form game, what's the Nash equilibrium, and maybe what is a zero sum? Just the definition. Raise your, okay. All right. So I'm gonna recap. No worries if you haven't heard this. But in game theory, there is this notion called Nash equilibrium, and there are different solution concepts, different forms of equilibrium. And game theorists are very fascinated about analyzing systems when they are at equilibrium. But then in real world, why we have equilibriums? In some situations, the equilibrium is not unique. So there are multiple equilibria. That's really a bad situation because even a game theorist would say, well, so this is a failure because even though I assume that people are at equilibrium, but there are multiple equilibria, so I don't know which one is the state of the system. But even in situations that there is a unique equilibrium, in practice, why we are at that state? And then one answer to that is that agents that are playing that game, they're running quote unquote learning dynamics, iterative algorithms that try to maximize the utility of the agent or minimize the loss of the agent, so on and so forth. And the belief is that, in many, many applications, in many, many settings, many, many games, these learning dynamics eventually converge to some sort of equilibrium. It might be Nash equilibrium, it might be a refinement of the Nash equilibrium. And this is indeed the case in many situations. So what I'm going to show you today, and then we are going to continue next time, is that there are certain pairs of equilibria concepts and learning dynamics that they work well together, which means that if the agents running those learning dynamics, they're going to convert to that particular equilibrium. And this is good news for game theory because then they can claim that, hey, equilibria are practical because we know these learning dynamics are going to converge. There are a lot of caveats. For example, in many settings, we don't know convergence to Nash equilibrium, we know convergence to refinements that sometimes they even don't make sense. That's one bad news, and you're going to see that in the next lecture. The other bad news is that many times, as I said, there are multiple equilibria, so it's not clear which one the learning dynamics converge to. Some of these equilibria are not as stable, that creates problem for learning dynamics, so on and so forth. So there are a lot of caveats to this statement. So you never think that in all the games, if I run a learning dynamic, I'm going to have a convergence equilibrium. That's not really the case. But we are going to try to find out some particular structured games that have that property. And the canonical example of which is what we are going to study today, which are zero-sum games. Zero-sum game is a two-player game that basically the sum of our utilities is always zero. If I win, you lose, and vice versa. I'm going to formulate that in a second. It turns out in these games, not only you have convergence to equilibrium if you run learning dynamics, there are certain learning dynamics that will give you super fast convergence to equilibrium. And there is not always a unique equilibrium, but there are learning dynamics that can steer you to different equilibria. It has been very well studied. So we know a lot about zero-sum. Beyond that, when we go to other normal form games, which I'm going to describe in a second, things become very complicated. But still, there are really powerful results that help us to understand the convergence of dynamics to those equilibrium concepts. With this brief introduction, let me do a super quick intro to game theory. Oh, one thing before I have to say, so here we're thinking about loss minimization, right? So the algorithm with minimizing loss. There is an analog of the whole thing here for reward maximization. I might actually post a note on Canvas to show you how to get the reward maximization. It's actually a good exercise. Essentially, nothing is different. The only difference is that you're going to start from weights that are 1. Every time that you see a reward, so every time that you realize some reward, multiply the weight by 1 plus epsilon to the power of reward. So rather than 1 minus epsilon to the power of loss, we are going to multiply by 1 plus epsilon to the power of reward. And it turns out that this algorithm, the max version of HEDGE, will give you a comparable regret bound, something like expectation of m divided by 1 minus epsilon, expectation of m times 1 plus epsilon minus ln of n divided by epsilon. I'm going to write it in a second. And it's not really that complicated. Another way of getting a meaningful bound that's slightly weaker than what I just said is assuming that the reward is 1 minus loss and then running the hedge for loss, which if the rewards are between 0 and 1, we can do that. But then you get a slightly different bound. And the algorithm is going to be different than the one I mentioned. In fact, they have different learning rates. But just keep in mind that it's not just the loss minimization that we can solve. We can also solve the reward maximization of the whole thing. And you can get a almost identical regret. All right, so a normal form game. Suppose we have n players. Each player I has what I call an action set, AI. Each player I has also a utility function. So they're trying to maximize utility. This is why I mentioned the reward maximization. As a utility function, let's call it UI, that maps A1 times A2 times AN to a non-negative number. Basically, think of it in the following ways: there are n players, they are picking action from their corresponding action sets, and then based on what I call the action profile of all the players, the selected vector of actions by all the players together, each player gains a utility. So the utility in principle is the function of the entire action profile, and in some sense, each player would like to maximize his utility. Like, for example, there are these games, when there are 2 players, you can describe the game utility nicely in a matrix. These are called bimatrix games. And there are some cute examples of bimatrix games. Let me mention some of them too. There's a game called Bach or Stravinsky. Who knows Bach or Stravinsky game? All right. So it's like I'm a fan of Bach and you're a fan of Stravinsky. And let's say you would like to go to the concert together, but you have different preferences about Bach versus Stravinsky. If we go to Bach concert, then I'm going to get a utility of 3, and you're going to get a utility of 1. If you go to a Stravinsky concert, I'm going to get a utility of 1, and you get a utility of 3. If it happens that we go to different concerts, because we like each other, so we're going to get 0, 0. That's the game.
I think this is more commonly known as Battle of the Sexes.
It's Battle of the Sexes as well. Yes. That's one game. Another game is Bach and Stravinsky, also known as Prisoner's Dilemma. So there's a situation that Bach and Stravinsky are in the same room, and they want to decide whether they should play their instrument at a loud level or quiet level. So we have quiet, loud, quiet, loud. The quiet, quiet is good for both of us. Actually, loud, loud is good for both of us. I don't know which one actually. Let me take a look at my notes. Each has a different interpretation. Yes, apparently we like quiet, quiet. But quiet, quiet has utility 3 and 3 for us. By the way, so if it's not clear, so when I say this pair, that means if you play this pair of strategies, then this is the utility of player 1, this is the utility of player 2. Think of a row player and a column player. So the row player gets the first utility, the column player gets the second. I should have said this notation. The quiet, quiet gives us 3, 3. Loud, loud gives us 1 and 1. And then if you're in a situation that I'm quiet, you're loud, then the loud player is going to enjoy it because it's playing loud and the other one is not intervening. So it's going to be 1, 4. And otherwise it's going to be 4, 1. Because it's a symmetric game. There is an analog of that related to two prisoners that they want to confess or not confess. So they have committed crime together. They don't know whether the other one is going to confess or not. If both of them confess, then they're going to go to jail for 10 years. If none of them confess, they're going to get freed. If one confesses, the other one doesn't confess, then the guy who confesses is going to have a small jail time and the other one is going to go to jail forever and vice versa. It's kind of like the same situation. And then the final game is called Striker and Goalie. It also goes by the name of matching pennies. So I'm a striker, you're a goalie, you're going to decide on left or right. Like soccer, so I'm going to go with either left or right. And you're the goalie, you do the same. If we both pick left, the goalie did the right thing, and he's going to get 1, otherwise he's going to get 0. And vice versa. So if I pick left, you pick right, then the striker wins. So this is the striker. So row player is the striker, column player, so this is the striker, and this is the goalie. So left, right, left, right. So left, left is bad for a striker, good for a goalie. Maybe -1, 1, and then right, right is the same. But the different action will be good for a striker. Good. So another game is zero-sum game. So zero-sum game is a 2-player game. 2 players. They have different set of actions. Let's call them, I'm going to call them max player and mean player for a second. It will be clear in a second. Mean player. So max player utility is basically some function u of the action of the first player, A, and the action of max player himself and the action of the other player. This is for the max player, this is for the mean player. And they have some arbitrary action sets. For the mean player, the utility is the negative of that. So it's like -u of A and B. So regardless of what action profile they pick, the sum of the utility is always going to be 0. So in some sense, one player is trying to maximize utility, the other player is trying to minimize. And we are playing this game. All right. Now, the Nobel Prize winning work of Nash tells us this particular note. Oh, before that, let me actually say something. So when we think about actions in games, you can define what I call a pure action strategy or pure strategy. So pure strategy is when I deterministically pick an action as a player. There is also the randomized version called mixed strategy when I pick a randomized action, the distribution, and you can describe that strategy by a distribution of actions. So pure strategy pure is just deterministic. Because this is not a coordinate game theory, I'm trying to be handy. So mixed is just a random stretch. Now the Nobel Prize winning work of Nash is tell us what is Nash equilibrium and its existence. In a normal form game, let me define pure Nash. The profile of the strategies or actions. I'm going to use these words, strategy and action, interchangeably. The profile of the strategies A1 to AN is a Nash equilibrium, abbreviated as NE, if and only if the following. For every player, for any what I call the deviating strategy AI prime in the action set of that player, utility of the player under profile A1 to AN be greater or equal than the utility of the player under a different profile. What is that different profile? Everyone else is going to remain the same, so they're going to play the same action, but then player I is going to deviate to a different thing. So AI prime, I'm going to use its notation A minus I, basically refer to a vector where you have A1, A2, AI minus 1, and then AI plus 1 all the way to AN. Okay? So that's a pure Nash equilibrium. You can also define a mixed Nash equilibrium, which is a profile of mixed strategies, which is a bunch of distributions. Let's use P1 to Pn is a mixed Nash if and only if the following is true for every player I and every deviating strategy AI prime in AI, we could alternatively think of any deviating mixed strategy. Pi prime in the simplex of AI. The following is true. Expectation of UI A1 to A1 to AN when AI is drawn from PI independently. So in the mixed Nash, players are playing independently. This is greater or equal than expectation of A minus I is drawn from P minus I, UI of AI prime, A minus A. So this is basically a random version of the previous statement. I assume that, let me use a better notation, so for every G, right. So on the left-hand side, I assume each player independently draws an action from their corresponding mixed strategy. On the right-hand side, all players except for I, they are drawing independently from their mixed strategies, and then I is deviating to, let's say, a deterministic strategy A. So if something is mixed Nash, you could alternatively change this right-hand side to mixed strategy, because if you are better than any pure strategy, you're going to be better than any convex combination of the pure strategy. So I could use this alternative definition, so they're pretty much the same. Right? And then Nash result is that I'm not going to explain the theorem in the most general form. In a normal form game, in a finite normal form game, when the action spaces are finite, in a finite normal form game, when the action spaces are finite and the utilities are bounded, let's say between 0 and 1, or whatever, they're just bounded, there always exists a mixed Nash equilibrium. It doesn't say it is unique. but it says it exists. And in some cases it can be unique, in some cases there might be multiple equivalents.
What would it mean that the utilities are not found? Like, how can they be not found then?
We can give you a wiki-backy weird utility that if one player is playing this particular action utility. There are results that speak to those quote-unquote degenerate cases, but for the simplicity of this lecture, I'm just asking you have a finite normal form game, everything is bounded, everything is well behaved, so that exists in this naturally. Back to our 4 games. So in Bach or Stravinsky, this is a pure Nash. You can check that. If we go with this pair of strategies, none of us has any incentive to deviate. This is another pure. Does anyone know the mixed Nash for this thing?
I think it's like a fourth and 3/4 average. There's multiple, right?
Good. So what are the multiples? 3/4 and 1/4.
There's
So exactly, if I play Bach with probability 1/4, let's say I'm a column player. If I play Bach with probability 1/4 and Stravinsky with Bach with probability 3/4 and Stravinsky with probability 1/4, then this is another mixed strategy.
And then the other ones are pure. So either you agree on Bach or Stravinsky, right?
Even you don't agree, it's just.
Or you're, yeah.
It's your
That's true. So the point in the support are going to be BB and SS. That's what you're saying.
Yeah, so there should be like a probability 1. You both do Bach.
No. So this is probability 1 we do Bach. This is probability 1 we do SS. These are pure equilibrium. And then there is a mix that this guy is going to play Bach with probability 1/4 and so Bach with probability 1/3. 1/3. No, so Bach with probability 1/4. Okay, so Bach with probability 1/4 and Stravinsky with probability 3/4. If I do that, then the other player is going to be different between playing Bach or Stravinsky, and that's something.
I forget, is there an argument that like pure is more likely to hold than a mixed one? No, I don't think
No, so there are games that there is no pure strategy.
so.
So
Right,
Nash the Nash theorem says that there always is a mix, but in fact, the striker goalie doesn't have a pure equilibrium, but it has actually mixed equilibrium, which is half-half between the rows. This game is a little bit different. So here you have what they call in game theory dominating a strategy for each player. So if I'm the row player, regardless of what the other player is playing, I'm always better off doing L over Q. Because if the other player is playing Q, my utility for L is larger than Q. If the other player is playing L, my utility is as much. So this is a weakly dominating strategy, same as the other player. Therefore, there is a unique pure equilibrium, which is the 1/1, and that's kind of like the essence of the Prison's dilemma. That it has a unique equilibrium, it's actually bad for both of them. If they were cooperating, like had a way of communicating, they could land here, but they are landing here in other. Yes.
Quick question for the above example.
Yes.
Edward. So because the utilities are sort of symmetrical,
Yeah.
why the probabilities are 1/4? Can't we just flip a coin 50% of the time?
No, so you need to make the other player indifferent. So the magic of 1/4, 3/4 is that my utility would be basically 1/4 times. So think of the other player, right? So the utility of the other player for B would be 1/4 of. Actually, you're, I think, right. So this should be 3/4 and this should be 1/4. So the utility of the other player for action B is going to be 1 times 3/4, which is 3/4. For action B is 1 times 3/4. So yeah, so if this player is playing B, my utility, if the player is playing this randomized strategy, my utility for B would be 1 times 3/4 plus 0. my utility for S would be 0 plus 1/4 times 3. So in both cases, it's 3/4. So therefore, this player is indifferent between B and S. So whatever this player does would be a best response. So now, if, as we said, the game is symmetric, so if I do the same strategy here, the same thing is going to happen. So whatever this player does is going to be best response. Therefore, these pairs, each one is going to be best response to the other one, and therefore you have a Nash equilibrium.
This randomized sort of thing is unique for this game.
No, it can, because deterministic but Nash is actually a special case of mixed Nash, right? So this is a counter example. So you have these are the pure Nash, these are the pure Nash, and then there is another pure Nash. That is a mixed Nash. So it might be very well the case that you have actually two complete mixed Nash equilibrium, none of them is pure. But in these cases, it happened. It didn't happen. In zero-sum games, it can happen. Because zero-sum games are kind of related to linear programming. So when the linear program has multiple solutions, you will have different equilibrium views. Okay, now we're going to focus on zero-sum games in the rest of the lecture. And we try to show running HEDGE by both players will help you to converge the equilibrium of the disk. Let me erase these parts. Theorem, which is known as, it has different names, but I think it is mostly associated to John von Neumann. So von Neumann, quote unquote, min-max theorem is the following. Consider a zero-sum game. Zero-sum game where max player action sets, let's say is the numbers 1 to n, and the mean player action set the pure action set is number 1 to n. So therefore, in principle, a max player strategy, let's call it P. If it is a mixed strategy, it's going to be simplex with n dimensions. And a mean player strategy that is mixed is going to be Q in delta M. For now, we assume that n and m are bounded for simplicity. And also, for every pair I and j of action profiles of the two players, I'm going to assume that u of ij is between 0 and 1, again for simplicity. If it is not between 0 and 1, but it is bounded, we can always apply a linear transformation by first shifting it to become non-negative and then normalize it to become between 0 and 1. And for the shifted game, the same pair of strategies would be equilibrium resolution. So this is almost without assumption. Then this is the von Neumann theorem. It says, if I look at the following max mean problem, so I'm maximizing over all p's in delta n, minimizing over all q in delta m. Let's say the expectation of u of a and b, where a is drawn from p, b is drawn from q. The max player is trying to maximize u, mean player is trying to minimize u. This is equal to if we switch the order of mean and max. Mean q in delta M, max in delta M, expectation of U of A and B. And each side has the interpretation. So this side has the following interpretation. Imagine that max player goes first, and then the min player goes second. So I'm going to pick P, and then in response to my P, the min player is going to play the best response by picking the Q that minimizes the expectation. So this is the version of the simultaneous game that is not actually a simultaneous game, to the Zuckerberg game, where the max player goes first. On the right hand side, it's the opposite. The min player goes first, picks the Q, and then the max player best responds by picking a P that maximizes the utility. And the Van theorem is saying that these two quantities are equal to each other, and they are equal to some number V, which we call it the value of the game. This is just a definition. So the value of the game. But not only that, number two, the solution of this min-max will identify the equilibrium, the Nash equilibrium of the zero sum. In other words, if P, think of a P that is among the maximizers of the Zuckerberg game where the max player goes first. So it is argmax of mean of Q in delta M, expectation of U of A and B, and Q is a minimizer in the other Zuckerberg games. It's arg mean of Q max over P in delta N, expectation of U of A and B. So pick any pair like that, then the profile P and Q will be a mixed Nash equilibrium. Right? So we're going to show von Neumann theorem. There are multiple ways of showing that. There is actually a connection between this min-max problem and LP duality. You guys have heard about linear programming and strong duality there. So this is essentially a strong duality in disguise. I'm not going to follow that route. But keep in mind that this is really like a strong duality. So what I'm going to do instead is to come up with a pair of algorithms that I can find the equilibrium of the zero-sum game when they are playing together. In particular, I'm going to assume player 1 and player 2, the max player and the min player, they are running two instances of the HEDGE epsilon algorithm with a particular parameter epsilon. And they're going to play the game in the following way. So as the max player, let's think of the min player first. As the min player, I'm going to play an action at this round. Remember the full information on learning is finitely armed. So my actions are my arms now. So as the min player, I'm going to play one arm. Then, based on the strategy picked by the other player, I'm going to incur a loss, which is equal to U of A and B for particular A that I have played in this round, and the B that was played by the other player. I have no idea what the other players do. This is why I kind of like assume that these losses for the min player are picked by an adversary. So play my strategy, then the result of the game will be revealed. I can compute how much loss I incurred, how much negative utility I incurred. I go to the next round, run the HEDGE algorithm again, draw another action, so on. So this is the min player. And then max player is doing exactly the same thing at the same time. And they play this game together in, let's say, capital T number. Is the sequential game clear?
You both have rational explications, like both of you know fully the game.
Yeah, so they know the structure of the game. So given the action of themselves and the action of the other player, they can compute the utility.
So like when you're saying like they don't have a sense of what the other person is doing, they have a sense of how the strategy that they would.
Exactly. So they don't know the other player's strategy in that round. Like I play a strategy, I incur some loss, and someone tells me what's the strategy of the other player that pushed me to incur this loss. But in fact, all you need to know is how much utility you lost in that round.
Right, yes.
Is the sequential version of the game clear? Right. Now, I'm going to make an assumption that these two players are running an instance of HEDGE. Let me be more specific. So, max player runs HEDGE epsilon. And as a result of that, it's gonna create a sequence of mixed strategies. Think of them as the p vectors in different iterations of HEDGE, which are, I'm gonna denote by P1, P2 to P capital. So what is the utility of this guy in every round? So at time t, utility of this algorithm, let me actually use reward. So the utility of this algorithm at time t for any action I, so this is time, this is action, would be equal to, this is the max player. So the utility, if this guy plays I, and the other player is playing a strategy, let's say B of t, where B of t is drawn from the distribution that the other guy is using here. That kind of the game from the perspective of the max player. So I'm solving a full information online learning problem as a max player. I play a strategy drawn from a distribution at time t, which is pt. Then I'm going to I'm going to enjoy a reward, which is equal to u of I and bt for any action I that they pick, where bt is drawn from distribution of the other player. And now you see why it was important in the previous analysis that the adversary is adaptive. Because, players see each other's past strategy. So in principle, the guy who picked QT and therefore influenced the reward I'm incurring in this round could look at my previous strategies and make a decision. So it is important that I have kind of an algorithm that can learn against an adaptive adversary on all my terms. So this is the game from the perspective of the max player, and then the mean player runs HEDGE epsilon, another parallel independent instance of HEDGE, and therefore creates a sequence of mixed strategies Q1 to QT. And this guy is the loss minimizer, similar to the previous part of the lecture when we were minimizing the loss. So at time t, the loss that this algorithm incurs for any action I is essentially U when the other player is playing AT and I play I, right? And AT is drawn from ET. So again, this is time. This is action. Action of, let's say, mean player. This is the action of max player. Yes.
So if from the perspective of the max player,
Mhm.
if I know the mean player runs as the distribution of QT, why should I do the hedge? Why shouldn't I just pick the action that maximizes my utility?
That's a great question. So if you knew that the other player is running HEDGE, and therefore you could guess that is QT, maybe you could do something better. That's amazing. And in fact, there are learning algorithms that will take advantage of that and give you faster convergence. I'm going to go with a more naive version that doesn't even exploit that structure.
So what the assumption here is that we don't know QT. Like the player doesn't know.
At time t, we don't know
Yes.
QT.
Uh-huh.
So first of all, even if you know QT, you don't know BT, right? So you don't know the exact realization. Because the other player is gonna draw an action independently from their corresponding distribution. I totally agree with you that in your head as an act player, you can simulate the other algorithm. If you knew if it is a randomized algorithm, it's going to be a little bit complicated because if it's a randomized algorithm, the only thing that you know is the distribution of QT, to be exact. But let's say for a second that the mean player was running a deterministic omega. So I could, in principle, I could simulate that algorithm exactly, and at time t, I know the distribution from which the other player is drawing an action. That's totally right. There's still two things. I don't know the exact action they're playing because they're going to play independently at that round from that distribution. So I don't know exactly my utility function.
I know
So
the
that actually let's
distribution.
respond.
I know the distribution, like the
Yeah. So you know the distribution. So you could play best response against this to maximize the extension. That's totally correct. Yeah, and if you do that, but if both players do that, then they're not going to learn. So they need to be a little bit stupid so that they actually learn the Nash equilibrium. That's kind of the option. But at the same time, there is a subtlety here. Being best responder is not going to help you with learning. Going with a naive hedge algorithm is going to learn, but at a slow rate. And then there's somewhere in between. There's an optimistic version of hedge that learns at a faster rate. Is somewhere between the best responder and hedge. I'm not going to talk about that today, but that's really good. And one other comment I can say is that even if one of them is learning and the other one is best responding, as you mentioned, let's say one player is learning, I'm going to draw an action, and even the other player sees the realization of my action and then goes with the best response. If one player best responds and the other one learns, at least you can show that both of them, they converge on average to a Nash equilibrium. I'm going to go with a simpler version when both of them are running hedge. But there is also that theorem. It was supposed to be part of your assignment, but now I revealed one of them.
Wait, so, I have a question.
Yeah.
Sorry. So this just requires that you play enough T.
Mhm.
Okay.
Yeah.
Gotcha. Alright.
So let's see why this is going to learn. Nash equilibrium of review. All right, so here's my claim. Claim, and I'm going to formalize the claim as I prove that. Claim, look at what they call the average plane. The P bar, which is essentially 1 over T, summation T from 1 to capital T of PT, and Q bar, which is 1 over T, summation T from 1 to capital T of QT. Then I claim P bar and Q bar is an quote unquote almost Nash equilibrium, mixed Nash equilibrium. And by almost, I mean the following. So basically, if I look at the utility of letting a max layer under P bar and Q bar, then I'm using a notation a little bit. So when I say utility of P bar and Q bar, in your head, take the expectation. That means I'm looking at the expectation of utility of A and B when A is drawn from P bar and B is drawn from Q bar. So let me actually define it once. So this is the expectation of U of A and B, where A is drawn from P bar, B is drawn from Q bar. So I'm going to show that this is greater or equal than U of P and Q bar minus a term which is going to be order square root of ln of n divided by t minus order square root of ln n divided by t for every profile p that is in delta n And then the other is that the U of P bar and Q bar for the mean player is also a good strategy. So it's going to be smaller than U of P bar and Q plus somehow the same term, order the square root ln of n divided by t plus order the square root of ln of m divided by t. And this is true for every mixed strategy of the mean player, deviating the strategy. This is what I mean by an almost mixed match equilibrium, right? So that means if the other player is playing Q bar, I'm almost best responding by playing P bar as the max player. If the other player is playing P bar, I'm almost best responding by playing Q bar as the min. Right? Let's try to show this. Oh, and what is the assumption by the way? So I'm assuming that they're running the hedge algorithm. So let me write down the guarantee of the hedge in case that you're not on the same page. So the guarantee of the hedge is saying that basically in this game, if I write down the guarantee of the hedge in expectation, I mean for the max layer, I know the utility I get, summation t from 1 to capital T, which is the utility of me under strategy PT when their player is playing QT, is greater or equal than so yes. So use at least the summation T from 1 to capital T, U of PT and Q minus a square root of, or 2 a square root of T and n of n for every strategy Q. So let's think about this for a second. Oh, I'm sorry. I'm so sorry. It's a QT for every strategy Q in delta n. So because I'm running a learning dynamics, similar to hedge, the utility I get from the frequency of plays I have, P1 to P capital T, would be at least the utility of the best fixed action, let's say the best fixed mixed strategy, minus some term. We already get characteristics for the loss minimization problem, but for the reward maximization, you're saying there'll be a square root of T times N. This is the guarantee of hedge that we saw, but for the reward maximization version, after you set epsilon properly. And then for the mean player, kind of the same thing. Oh, and this N is this. For the mean player, I know that the summation T from 1 to capital T, U of PT QT is essentially at most summation T from 1 to capital T, U of PT and Q plus 2 times the square root of T times ln of m, ln of m, right? For every Q that is in the simplex with m image. That's exactly the rigor bound that we had earlier. Alg minus m, x of a minus x of m. This is exactly that quantity. Because mean player is trying to minimize the loss, and the loss is the utility that the other player has. All right, so now I want to show that. Let's start by expanding U of P bar and Q bars. So U of P bar and Q bar, you can say, is definitely greater or equal than minimum over Q of U of P bar and Q. And this is equal to the minimum over Q. So now that I'm fixing Q, U of P bar and Q, I think the answer is going to be right. So imagine done. So I claim the U of P bar and Q is basically equal to 1 over T summation T from 1 to T U of PT and Q. I'm not using any magic. This is kind of a blind affine game in the sense that, what does that mean? So that means that, hey, I'm going to pick one of these distributions, 1 to capital T uniformly at random. And then I draw a strategy from the corresponding PT that I run. And then I take expectation. This is just saying, well, so now let's do the following. Let me first uniformly at random pick T, the index I'm focusing on. Then I'm going to draw a strategy from PT, and then I take the expectation. We can swap the order of the two expectations because of the linearity of the expectation, and therefore it will be equal. And then this is greater or equal than, okay, now, let's see what I'm going to do. So I think now I can say this is greater or equal than 1 over T summation T from 1 to capital T U of T and QT using the guarantee of the mean layer minus order square root of log M divided by T. So look at the right hand side. The right hand side is basically the loss of the mean layer when runs the HEDGE algorithm. This is the best loss that the player could get by playing a fixed strategy Q. And we know that the difference is bounded by a square root of L and M times T. Now this is average over time, so this T comes here, and therefore the inequality. So here I'm using a star, and a star is basically this guy. Is it true? Now I'm going to use the guarantee of the max player. So this at the same time is going to equal than 1 over T some it's going to equal than max over P from 1 over T from T from 1 to capital T U of P and QP minus order the square root of ln of n divided by t minus order of the square root of ln of n divided by t. What did I do here? So here I use double star, which is the HEDGE guarantee of the max player. Right? So the other player is playing QT. From my perspective, I'm playing the sequence P1 to P capital T, and I'm fighting against the fixed strategy P. So my total utility would be at least that amount minus some bigger amount. Does that make sense? All right. So we're almost there. So now, Now, this can be written down as max over P 1 over, so what is this? It's like, I'm the max player, I'm playing P, and then the other player is playing QT at every time, and then I'm taking an average. This is equivalent to a one-shot game when I'm playing P, and the other player is actually playing the average strategy. Remember the argument here? So exactly the same argument here, so I'm going to rewrite this as is equal to the U of P and Q bar minus the two terms of it, which is ln of n divided by t minus order ln of n divided by t. Now you can see an inequality which is pretty much similar to the deviation inequality, the definition of a Nash equilibrium. So the claim was that, okay, so I proved this, that if I'm playing P bar, the other player is playing Q bar, my utility is going to be greater or equal than any other deviating strategy if the other player plays Q bar, minus some term that eventually is going to be pretty small. Why? Because if I let t go to infinity, then this term converges to 0. As a result of that, you can say in the limit, this is greater or equal than that. So as the max player, I'm best responding to the mean player. The other inequality is identical. Basically, you start from this, and then I'm going to use the max of P, U of P and Q bar, unlike the other version. So there's this other version that says U of P bar Q bar is at most mean over Q, U of P bar and Q, plus order square root of ln of m divided by t, plus order square root of ln of m divided by t, in order, which I'm not going to repeat. Oh, you are over here. All right, so this is going to be a almost mismatch equilibrium. Also, an artifact of this is basically the following. So imagine these terms are going to be 0. Now, if you combine this with that, then this basically says that you have found a pair of strategies such that minimum over Q, okay, let me write it down. So let's take it to epsilon, and I'm going to put that in like a minute. If I put the two things together, it basically says that minimum over Q of U P bar and Q is greater or equal than max over P. So this is 1, this is 2. So by 1 and 2 together, minimum over Q, U of P bar and Q is greater or equal to max over P, U of P and Q bar minus 2 epsilon. Now we have a proof of the first bullet of the von Neumann, because this is going to be greater or equal than max over P mean over Q U of P and Q, because switching from P bar to the best strategy of the first player who goes first, it only increases the utility. On the other hand, this is going to be greater or equal than mean over Q, max over P, U of P and Q, minus 2 epsilon. And this is really like the hard direction of the von Neumann's equality. So the first bullet, that the mean max is equal to max mean. So when epsilon goes to infinity, which is equivalent of t goes to, epsilon goes to 0, which is equivalent of t going to infinity, then the max mean would be greater or equal than the mean max. And this is the harder direction for showing this. In fact, the other direction is almost trivial, showing that mean max is larger than max mean. Do it as an exercise. This is weak duality versus a strong duality. So mean max greater than max mean. If you weak duality, this is strong duality. So these together with the one that I'm gonna leave you as an exercise, this plus the easy direction of the von Neumann, basically prove the two things that we want to show. And first of all, there's a min-max theorem here. Max is equal to min-max. And second, basically, yeah, so you can see from this also that if you pick a maximizer when you're replacing Q bar, and here you pick the minimizer when you're replacing P bar, then this is gonna be giving you an equilibrium. Yeah, so you need to write it down to see exactly how that inequality would be translated to, but it's almost true. Yeah, thank you so much. Sorry, I don't deliver it like that.